Now let's look at the last example. The previous example, we focus on only previous example. What we want to know is in terms of the strategy, which strategy gives you the best result. But we still that's the for the strategy. But what if what we want is in terms of the number of investment that we need to buy. Say we have two stock A and B, and we have two stock price that change over time, SA and SB, that are different, changing differently. And A and B are the number of units that you own, you have purchased. And WT is the function of wealth, meaning that you can just multiply NA with SA and B with SB. Combine them, you get the total amount at time T. Okay, so our assumptions here in terms of portfolio is that we'll just invest one time and then leave it at that, right? No trading between 0 to T to the time that we have here. And initial time, T0, we have NA unit of B and B unit of B. We have initial wealth of W0 that comes from multiplying the price with NA, multiplying the price of B with NB, and then combine them. For the terminal at time T, we have NA and NB as well, but we multiply at the price at time T. Okay, now we have initial point, we have the end point, right? Now we are going to take a look at something fun that our simulation will come in. This is called the Brownian motion, right? The Brownian motion, let me open this and show you. I'm not sure if you hear it, so let me try it out. Let me try it out if you hear it from my computer audio. Let me check. It get the microphone, speaker. Let me check the audio setting. Let me try it. If you did not hear it, then tell me. Do you hear the sound?
One thing that's astounding about...
Do you hear the sound? Yes, okay, good. Right, let me show you this video. It's quite good in terms of explaining Brownian motion.
One thing that's astounding about Einstein's publications in 1905 is that they spanned such a large range of physics. After illuminating the quantum nature of light by explaining the photoelectric effect in March, April saw Einstein turn to something apparently more mundane: particles suspended in fluids. In particular, if you look at tiny particles in water or dust motes in the air, you'll see that they jitter about in a very odd and random way. That is, it appears odd and random unless you believe that the air or water itself is made up of even smaller particles called atoms or molecules, which just bounce off of each other according to very simple rules. This is called Brownian motion, despite the fact that botanist Brown wasn't the first to discover it, and similarly, Einstein wasn't the first to describe it mathematically. But he did draw the conclusion that the mathematical description of Brownian motion is evidence for the existence of atoms, even if you can't see them directly. And then he cleverly derived how big atoms should be based on how much the Brownian particles move. That's like measuring the size of a penguin just by looking at how icebergs jiggle. Talk about cold and calculating.
Right, this is it. Let me come back to my slide. Okay, the Brownian motion. Actually, you have seen the explanation on that. In terms of the usage of Brownian motions in modeling, in stock price simulations, because the stock price change quite randomly from the effect of various factors, from the demand and supply of that. So people have been trying to model the change of the price using the change like Brownian motion, that is the change of one location of particle depending on this location, and then it can randomly go around. It is explained as a random walk, just like this one. And we can do it by simulating the change with respect to the current point, just like the last example. Okay. So to do the Brownian motion in terms of stock price, we can do two things. First, simulating the change. Second, postulating the change into the distribution, right? So we use this something like this one. The above here is the change in terms of the distribution. That is, instead of just explaining the value as the value itself, we put the change into this. This is like the normal distribution equation. You can refer to the normal distribution equation. You get the initial, you get the value multiplied here and the exponential values that would scale this value. It will change this value up and down. So that means you have the starting point, and this would explain the change, whether the exponential part here would go up or go down, depending on the change in BT here. Oh, and the BT here is calculated from the Brownian motion. That is the current position, depending on the previous position, plus the change. And the change comes from random of the normal distribution, just like that. Okay, so we are doing that here. So to do that, what we need to do, if you write a program in auto language, this is in MATLAB, but I think it's a good pseudocode here. Actually, it's not in MATLAB, it's pseudocode. You need to set initial position, t0 equals 0, bt0 equals 0. And then from that, we can iterate, right? Generate x, which is sampling from normal distribution, mean 0, and the change variation equal t1 minus t1 minus 1, ti minus 1. And use this x add to the as to the Brownian motion. This would look like this graph, right? It's kind of going random. Right? All right, then we can incorporate the change into the probability. Using this and then put into the probability, you put into STA and STB, and then we can evaluate the number of times the event occur. That event is the wealth is less than initial wealth, right? By 90%. Suppose we want to see what is the probability of the price of the worth or worth drop by 10%. We use Monte Carlo, right? Monte Carlo means repeat lots of time. For each time, we can compare if the worth is less than 0.9 and then repeat it a lot of time, right? If it's less than 0.9, if it's the worst, above is the worst at time t, the worst at time 0, less than 0.9, count it as 1, otherwise as 0, and then sum them all, divided by the number of runs. Okay. Now let's try it out in code. So to try it out, say we have the time t equal 0.5 of years, and that's for the exponential part, the change in the price. And we have the mean of the mu A 0.15, mu B 0.12, sigma, these two. This is for the mu A and mu B here. Think of that as the standard values of the change, and this is the actual price and the number of units that you hold initially. So by multiplying NA and NB with the price, you get the total initial worth. Now let's look at the change. So to simulate this change, we need to generate Xi and the price, and then compute IL for each Xi, and then repeat it lots of time, capital N time, and then calculate the expected value of this projection. Okay, how does it work in R? Right. So in R, let me explain the code here. First line here, I just initialize the results list to be null so that it can be concatenated later, and then calculate the mean out. So this is the list that will contain the result. And then using capital N equal 1000, number of simulation runs, the time that I will repeat the experiment. And the parameters that I have here, number of points, this is the resolution of the change, 1,000 times in the half years. So just the resolution of the change you can increase it for accuracy, or you can just change for, so this is, if this is half years, you can change the value to 180, right? 180 means 180 days, half years. About that. Or you can change it to say 180 times the number of hours that the market open, 8 hours a day. And then you measure hourly basis, right? So I just used 1,000 for a simple explanation here. And this is the time, it's 0.5, and A and B, and the price, and the parameters of the change. And the initial worth is NA times S0A, and B times S0B. We get initial worth. And here is the repetition of the time that we have here for Monte Carlo for n, capital N time. What I did is to calculate B1, right? But instead of creating another loop, I just use the R norm. This is X in the example, in the slide, random of n from 0 and 1, because the difference between point is 1, and using cumulative sum, because this cumulative sum works just like this equation. This equation is actually accumulative, right? It is actually a cumulative sum, because the value at t minus 1 would come from the value at t minus 2 plus x, which is independent of another one. It would come from the value of t minus 3 plus x, meaning if you have x, you can just get the cumulative sum out of each, and then you get the B1 for the Brownian of stock 1, B2 for the Brownian of stock 2, and then you can put the Brownian motion into the price of STA and STB. You can plot STA and STB out afterward, and then see the change in price. You see that it works as random walk. All right, and then calculate the WT. You get the projection out, and if the projection is less than 0.9, right, you get P, which is the probability of the projection less than 0.9, and put it into the rest, right, into the result list, and then keep doing that for 1,000 times. We have like 1,000 experiments, and to evaluate whether this strategy is good or not good, or whether holding it in this amount is good or not good. All right. So let me share our code for that here. So this is the R code that I explained. Let's start with 10. So this is the strategy to evaluate the drop. Right? We want to know the probability of the 10% drop in the asset. Okay, and with 10 times you get 40%. That's bad. 20%, 29, 44. The value change every time you run, and that tells you that the number of iteration is not enough, right? Because you can see that there's no just that the value does not converge to just one value, and if we increase the number of iterations, it becomes 0.3, 0.2 to 1,000. It becomes 0.3, about 0.3. What does that mean? It means that if you go with this allocation, there's a chance of 10% that 30%. The chance of 30% that your worth would drop by 10%. Okay, that you will be poorer by 10%. 30% of that. Okay, so 30%. If you increase it to 10,000, the value would be a lot more stable. But again, you see that it requires lots of time to calculate, and the value would be kind of saturated to 0.28, 0.29, about that. So here is the Monte Carlo simulation that used to simulate, you can see it used to simulate the price, and then you repeat it a lot of time, then you get the projection of the strategy. Okay, let me go back to this. After trying out lots of time from 10 to 100,000, you can see the change from probability of the 10% drop change and then converge to specific value. Right? So with Monte Carlo simulation, you can simulate what would happen. You can estimate the parameters. You can estimate the probabilities, right, of the chance that things would happen here. Okay. So now let's. If you do you have questions for us about this one, because these are all of the contents here. Afterward, we will take a look at the lab on the thing that you need to do, which are quite simpler than this one. Okay. All right. If you have questions afterward, ask in the group. All right. For now, let me switch to the lab, to the thing that you need to do. You open it first. Not this one. Right.